Okay, we're almost to our seats, so we'll get started. I'd now like to introduce Professor Bill Skinner, who is the PRIF Consortium Program B leader. Bill is a research professor at the Future Industry Institute at the University of South Australia. Bill has over 30 years of experience in surface science research, with 24 years in relation to minerals processing. Bill has been with the University of South Australia since 1992, working on physical and chemical processes at surfaces and interfaces. In particular, mineral and materials surface chemistry, together with forensics, environmental science and biomaterials. He is also a frustrated guitarist and loves a gin. Bill, his words.
Who isn't these days? Okay, Program B. This is a different take on the diagram that you've all seen, but it, oops. Yeah, I did, and all right. Locking the two programs together, the division is pretty arbitrary. It's pretty much at the mill, mainly because the feeds to the mill need characterising and checking for variability, tracking, etc. And then the subsequent result of that is the product out of the mill, which then goes through to the processing. There's some generic challenges there. Certainly in Program B, maximising mill performance in relation to and as a function of the type of ore that's coming through, and particularly in terms of throughput, mill health, and product qualities. In flotation, we're looking at understanding pulp chemistry and the interactions with particle size and using sensors. And also in the leach circuit, looking at key chemical factors like ferrous-ferric ratio, eventually uranium sensing, etc., and looking for those key elements that cause issues in particularly tank leach. So the key across the two programs at the bottom, reduce variability and enhance the ore qualities going to plant. And then when you've got that plant, you want to maintain the performance of that plant, given now you've got more certainty in the ore qualities feeding that plant. Again, the projects in Program B are roughly broken into comminution related, flotation related, and leaching or solution measurement related activity. The major sponsors or major translation partners in this are Manta Controls and Magato. Manta Controls have developed a range of particularly acoustic monitoring and particle sizing in relation to mills, both vibration and direct acoustic. And Magato, stranger to nobody, grinding mill media, but Magato also possess a pulp chemistry monitor which will act as a platform for testing of sensors at site, connecting at various streams. So what are we trying to do, and what does success look like when you bring these all together? I mentioned variation, variability. If you can get the variability of ore coming from the mine to the plant down, you're much more able to see improvements and detrimental effects within the noise, and by virtue of that be able to make improvements on them. So you have more confidence on improvements you make in the process across the value chain. So things of ore properties, things like grade, the value mineralogy and relate associations, the hardness, which will then tell you a lot about what the mill has to do. Problem gang, being forewarned of that, which can inform not only the flotation process but also the leach process, particularly in gelling. The particle size, again, get a hard ore, comes through the mill, the particle size is off. So your hydrodynamics have to change if you're going to counter that, but you've got to be forewarned that problems are occurring. And hopefully the outputs at the end of all this is much more consistency in your process from woe to go, the ability to make decisions based on thresholds maybe set by economics, cost of energy, etc. And also making decisions based on the ore properties that will help you decide which process to send your ore to. Again, based on thresholds and economics. And in the end, always reduction in footprint, particularly use of energy and water. So this is the program for the afternoon. A long one, a riveting one. You will all be very, very excited. As I said, we've got a range of talks from the comminution through to flotation, through to leaching and solution measurement. I understand that the honours students' presentation will be quite entertaining. A bit tag team operation, I think, going on here, or a 5 by 100 relay, I'm told. So we look very, very forward to seeing that. So thank you very much, and I hope you enjoy the program this afternoon. Cheers.
Thank you, Bill. You've got some chockies as well. You do. They don't have Jimmy.
So the first of our PhD students for Program B is Kwaku Boateng. Kwaku is from the Future Industries Institute at the University of South Australia. His project is sensing and optimisation of autogenous and semi-autogenous grinding mills. Kwaku holds a Bachelor of Science in Minerals Engineering and Mechanical Engineering from the University of Mines and Technology in Ghana and the Thai-German Graduate School of Engineering in Thailand. Outside of work, Kwaku enjoys listening to music, reading, playing football, playing FIFA and surfing the internet. Kwaku.
Thank you very much, Dr. Shao. Good afternoon, everyone, and welcome to today's presentation. My name is Kwaku Owusu, and I'm here today to give a talk on my research project, which is titled Sensing and Optimization of the Autogenous and the Semi-Autogenous Grinding Mill. And I'm being supervised by Dr. Asamoah, Professor Zanin, Professor Skinner, and I also have two translation partners in the persons of Professor Crete from Magato and Mr. Karajogos from Manta Controls. As part of the Integrated Mining Consortium, my project is within the Program B Downstream, and I'm working on the combination circuit, and to be more specific, the AG-SAG mill optimization. Since the introduction of the autogenous and the semi-autogenous grinding mills, there have been a continuous growth and preferred application in the mineral processing industries in relation to the grinding circuit, with huge or significant benefit in terms of high tonnage treatment and operational economics. And the AG-SAG mills are basically cylindrical drums that are characterized by their large diameter to length ratio. And the purpose of the mill is to reduce large ore size into from several millimeters to preferred micron sizes. And the major challenges that are usually associated with the autogenous and the semi-autogenous mills are the high energy consumption that is coupled with real-time monitoring and challenges, real-time monitoring and control challenges. And towards the development of an improved and more efficient online monitoring system, the main objective of my project is to optimize the AG-SAG mill performance through real-time acoustic monitoring. And I would like to first of all talk about my major research findings. The first one is that we have been able to observe that different mill feed hardness can be detected using the mill acoustic response. Again, we have also observed that a sudden change in the mill feed ore size can also be detected using the mill acoustic response. And finally, different mill pop solid loadings can also be detected using the mill acoustic response. And why are my findings very important to the industry? First of all, we are looking at a sag-axe mill system where the feed material, which varies in terms of hardness and size, affect the mill processing in terms of it introduced inconsistencies and their fluctuations. And then there's no real-time monitoring of the mill feed hardness and then the particle size, the feed particle size. Usually it's done, the measurements are done outside the mill. Again, the mill solid loadings changes during the grinding period, and it's also difficult to do real-time monitoring, and then it goes a long way to affect the mill performance. And obviously, the mill is high energy intensive operation, and there is a need for a continuous optimization approach. And we are looking at a system which is a hostile environment, very harsh environment. Therefore, real-time measurements are very difficult to be done with regards to the ARC-SAG mill system. And there's also a problem with the internal measurement because we are not able to see inside the mill. So the proposed method is to go with the acoustic-based sensing technique, which we've realized that is a promising approach. We would like to talk about, or I would like to talk about some of the sensors that are available. The first one I would like to talk about, you have inbuilt sensors, and sometimes you have contact sensors, and these are very useful for monitoring the mill performance. But some of the challenges that are associated with some of these sensors are, we can talk about frequent maintenance because of the harsh environment of the mill. We can talk about the sensor drifting sometimes, the frequent calibration, sometimes very expensive, then mechanical breakdown. We are all looking at the harsh environment of the mill, and sometimes unreliable. And there is another traditional way to measure the mill performance in real time, that is to go with the traditional method. And that one is to listen to the mill noise and then make inferences. But it's also useful, but then the experience, we require a very experienced operator, and not reliable, is prone to human error. And our method is to use an acoustic sensor, which we realize that it's non-contacting. Therefore, there's no way the sensor can have access to the mill, and it provides qualitative and quantitative measurement, and then we can have a real-time monitoring, and then it's relatively economical. So what we actually did was that we are looking at three important parameters that can contribute to the mill performance if not well controlled. The first one is the feed size. We vary feed size, and then we also varied pop solid loadings, and also finally we varied the mill feed hardness. So what we actually did, our environmental setup, which was done in the lab in a controlled manner. So for example, we have the feed size variation. So we put in the feed, and then all other parameters being constant, like the feed is the rock material or the ore material, the water, the steel balls are constant, the speed, and then we run the mill. And so what happens is that you cannot appreciate the internal dynamics of the mill. So that is just something to have, you appreciate what is going inside the mill. So the interactions of the balls, the ore material, coupled with the liners, will result in excessive noise, and these noise are measured, and we are able to analyze and interpret the noise to make inferences to the mill and achieve some performances. So regarding the feed rock hardness that we considered, the two rock hardness, that's the model quartz and then the model calcite, we realized that once you put everything under the same condition inside the mill acoustic emission for the two minerals are different. And it's happened, it continues even when you increase the grinding time. But there is a bit of changes in terms of when you start grinding, you realize that the hard material, which in our case is the model quartz, tends to produce a lot of noise as compared to that of the model calcite. But as you grind further, because of the difference in hardness, the dynamics change. But the interesting thing that we have found here is that we are able to distinguish the two different mineral hardness using the mill acoustic emission. And the other side, this side of the graph, is a direct opposite of what is happening here. So the one here is the emission, and the other one is the absorb. So once you are able to emit, the more you emit, in the other side is the less you absorb. Again, looking at the feed size variations in the male acoustic emission, we tested about 9 different feed sizes, different size classes, and we realized that as you increase the feed size, you tend to increase the male acoustic emission. And then the other side, we did hetero-side feed, where we compared blend ratios, and we also realized that the male acoustic emission is being influenced by variations in the proportions of the feed size classes that we tested. And finally, the pop solid loadings that we tested and their acoustic emission, we also saw that there is a significant variation as you increase the male pop solid loadings. And once you do that, the male acoustic emission also changes. So we actually tested the beginning of the experiment, the first 30 seconds of the experiment, and we compared it with the last 30 seconds of the experiment. What we realized that we're having similar trend. However, the first 30 emission from the varying the pop solid loading tend to produce higher acoustic energy. But then as you reduce the size, the dynamics changes. But the trend in terms of increasing the acoustic emission as you increase the pop solid loadings is the same or have similar trend. So what we intend to do for our future work is that the experimental setup where we use a laboratory-based mill, the mill is something that we modified from existing magnetic ball mill and that of the standard Sakib mill for SPI test. So we intend to carry on laboratory-based methodology so that we can have some characteristics of that of the industrial operation. And finally, we want to carry on predictive model using machine learning algorithms where we will consider the feed hardness, the feed size variation, and other parameters. At this stage, I would like to acknowledge my supervisory team, the industry partners, FEESTEM, UniSA, Government of South Australia, PRIF Consortium, and BHP and all other sponsors involved. Thank you very much.
Any questions? Bernie Az is our roving mic this afternoon. Louw.
Yeah, hi, very interesting talk. I guess you've identified that there's a number of factors that are going to go in that, using your acoustic measurements are going to help you to predict and control the mill. Have you considered whether in a dynamic situation, having the sort of a priori measurements of both hardness and particle size and things like that, whether that can then go in a data fusion type model to further enhance the measurements and results that you're producing from the measurements?
So you mean the feed size variations or the particle size distribution?
Yeah, basically, if you were measuring the feed size variations or had a dynamic measurement of hardness and things like that, obviously when you're controlling for those by putting in either different size particles or different hardness materials, but if you had a dynamic measurement of that, you can incorporate that then into the model as well in addition to the acoustic measurements.
Yeah, that's right. So the major purpose of, the main purpose of what we did was to easily identify a sudden change in the feed size. So, and we are working in a laboratory-based system where we don't have a continuous operation, it's a batch system. But then the result that I have shown here is the very early stages of grinding that we want to appreciate a sudden change in the when there's a sudden change in the feed size variation. Is there a sudden change in also the noise? So as you rightly said, going forward in our modeling, we would like to incorporate some of these things here to make our modeling more robust.
Yeah, it sounds really interesting. Thanks.
Yeah, thank you.
Jose from Moss Minerals. Yeah, very interesting work. And kind of a related question, I suppose, just in terms of hardness. Have you considered doing different blends as well to see the impact of soft ore and hard ore?
Yeah, thank you very much. We've actually done such work where we realized that the blend ratios from different feed hardness also contribute to the mill noise emission. But then for the purpose of this presentation, I decided to just show the distinct hardness, just that. But we also have results for the blends. Yeah, thank you.
Time for one last question. Yeah, yes, coming.
Thanks, Kwaku. How, in terms of your time and money kind of input, how hard is it going to be to create a continuous, lab-based setup? Because I think that long-term data where you see shifts or a baseline change or a step change over hours is going to be really interesting, and I think that's what, when I picture this operating and control system for a mill, is you're going to come in one morning and see a step change down in acoustic side, data, and want to go look why it happened, or you might now know what to look for.
So if I understood your question very well, what I can say is that at this stage we are doing fundamental studies to really appreciate the relationship between some of these very difficult to control parameters inside the mill in real time and acoustic. So we've kind of done some work varying a lot of parameters, and we are seeing promising results at the moment. So we kind of cannot conclude on some of these things, because these are fundamental things that we are doing. But the good thing is that we are seeing very distinct or promising results at this stage of the work that I'm doing. So we hope to further work will kind of help to integrate it in the real-time situation. And as you said, in my case, I did batch system. Yes, batch system at the moment, but we're trying to kind of mimic in what we're trying to do in mimicking the industrial performance, like in a continuous mode, is that what we can only do in the lab with our small scale mill is to do a lock cycle. So we kind of lock cycle the operation and see it's not going to be complete like the continuous system, but at least we will appreciate some trend in the continuous mode, and that will also be something very good for future or for the industry. All right, thank you.
Thank you.
Thanks, Kwaku. That was a good presentation.
Now we have our honours quintet telling us about predictive machine health monitoring for semi-autogenous and autogenous mills as part of Research Project 2. This project has been conducted by the 5 honour students from the School of Mechanical Engineering at the University of Adelaide, and they're supervised by Dr. Louw. We have Pranay, Tosan, Khaled, Sakib and Haodong, who are international students, and they're also on the lookout for graduate programs if anyone has any. I should just remind you, make sure you speak into the microphone. If you don't, online can't hear you.
Yeah. Who's going to change?
Speaks that. Yeah, just change on you.
Which one is it? Is it?
Green one.
Yeah. Hi guys, and welcome to the presentation on online health monitoring of semi-autogenous grinding mills, also known as SAG mills. I would like to thank Kwaku for the introduction, because now you guys know something about this. I actually don't know how this works.
Green.
Where do I point it? Yeah, okay. Anyway, that's the honors team. We've been called a boy band before, but there's not going to be any musicals. Our project supervisor is Dr. Louw, and our sponsors, PRIF Consortium. Now, our project motivation is to ensure that ensure that the SAG mills operate steadily. These SAG mills rotate and they grind ores into smaller pieces, and the liners inside of them are constantly bombarded with materials, so they actually get damaged over time. So we want to detect critical issues with liners before they even arise, and we also want to reduce maintenance cost because of that. There's a company, a Dutch multinational company, that have implemented their own system, their own online health monitoring system, and the results of those are as shown. They have reduced their critical impact by 45%.
their mill power by 30%, and their process variability by 6%. Now, as you can see, the maintenance of these liners is quite dramatic. They have to stop the production, which costs the companies money. They need labor, they need specialist tools, and also, as you can imagine, like when the production is halted, the process in the factory, the company's losing money. So that's what we want to avoid, and that's why we want to build this online health monitoring system. Onto the project methodology.
So, is a little too short. So for the project methodology involves three main tasks, and the first task involves developing a mathematical model in MATLAB and Simulink, and also calculating parameters such as the power draw as well as the particle size distribution, and then comparing those parameters to input parameters that are obtained from a specific mine's location. The second one involves the physical model, and the first aspect of the physical model is creating 3D CAD drawings, and then the second part involves performing scenario-based analysis on the manufactured 3D model. Then the final one is the predictive model, and which is the final task for the project, and it involves getting the results from the mathematical model, then combining it with the vibration analysis conducted on the physical model, and then forming a real-time health monitoring model known as the predictive health model. So the mathematical model. So what is the math model for the signal? So the math model is a flexible and powerful dynamic simulation tool or approach that's used for studying the dynamic behaviors of grinding circuits or comminution circuits. And it also helps in process optimization as well as in fault diagnosis and detection. So these are the 5 aspects that had to be initially described first in order to have a very comprehensive math model. So it involves the energy and the frequency of breakage events and their relationships to the charge. Also involves relationship between the slurry holdup and its discharge rate or flow rate out of the mill. And the classification of the performance of the grades is also another aspect that had to be described, followed by the particle size distribution of the product. So these 5 aspects all together make up everything that encompasses everything of the mill. So inputs, that's things that goes into the mill, the ores, things that goes on within the mill, there's the processes, and then the exits through the grades of the mill as final particles. So the math model is broken down into 3 parts. These 3 parts form the key findings for the project. And the first one involves calculation of the mill inside content and the discharge material. The second also involves using the Morrow and Austin power models to find the power draw involved in the mill. And the third is finding the particle size distribution by using the Witten's perfect mixing model. So when all these 3 aspects are combined, we can now develop a comprehensive or dynamic model that can predict both the grinding charge as well as the power draw under a variety of conditions. For the model structure, this really formed the basis for the Simulink that was developed, but it's much better to show it in a written form rather than just a Simulink filled up with MATLAB function blocks. So the first aspect is the input, and the input is gotten from the Fimiston gold mine in Western Australia. And the input is divided into 2 parts, the mill operating conditions and the mill design characteristics. And after all the inputs identified, the next phase is the initial charge, which involves the ores and the grinding media or balls. And then next is the grinding charge loop. The grinding charge loop is a massive iteration process that's used for finding the mill charge volume as well as the power draw. And the grinding charge loop has numerous parameters and operational variables that each have their own first order differential equations that have to be solved in order to find the power draw and charge volume. So after that is completed, the next is the mill discharge loop. And the mill discharge loop is strictly just for mill discharge. And once all of this is complete, that completes the entire cycle. So the next phase is the physical design.
And the teams will develop the 3D physical model on each component of the segments by the CAD software, and generate engineering drawing for the 3D print and the manufacturing. For the models, we have designed with the gear, shell, basis form, and the bearings, and also liners. The video shows the relationship of each part of the segments. Everything will all assembled to the on a steel basis form. The core of the segment is all spoon liners, and the 3D input and output shells will rope the output liners. The big gear will connect to the output shell by the screws. And also the input and output shell will connect to the basis form by the two bearings. And the big gear will relate to the smaller gear, which on the motor shaft to drive the main body to rotate. Yeah, and next one is the vibration assessment.
So for our initial analysis, we have taken these apparatus, oscilloscope, DC motor, charge amplifier, and our own sag mill, and our wired accelerometers. So for our initial testing, so we tried to find a specific position to put our accelerometers on the mill. So we came to the conclusion that we're going to put the accelerometers on the bearings that after taking several results, and these results were more accurate than the previous ones. So we have decided to put it on the bearings on both sides. And so for our analysis, so we take out the liners. So the liners are machined with the steel materials, and these liners produces vibration on the surface of the mill. So it can be altered around by using the input voltage and controlling through the DC motor. And so for our analysis, we have taken two scenarios where we can use the liners, like removing the liners, certain number of liners, and we can use the damaged liners to get our results. So for our vibration signal results, so I want you guys to hear these two videos properly, so you can check the noise level of the sag mill. So for this one, we have taken the two liners out from the opposite side of the mill. So just just listen to it carefully. So that was the opposite one, and this one. So we have taken the two liners from the same section of the mill, and the noise level is obviously different. So what we have come into conclusion that the weight distribution around the mill after removing the liners from different position has affected the noise level, and which also has affected the vibration and around the structure of the mill. So for our first waveform diagram, so this is the waveform of the mill with all the liners present inside the mill. So the amplitude and wavelength have been consistent for one rotation. However, for the analysis, we have taken the liners from the same section. This was the result that we got. So the halfway through the rotation, the wavelength and amplitude have been somewhat consistent, but when it comes to the position where the two liners have been removed, the position, the wavelength and the amplitude gets distorted. And for the opposite side of the two liners, the team has have been kind of analyzing through this one, and we came to the conclusion, it's just a practical conclusion, that that the weight distribution has affected the whole signal, and we come to the mathematical model results. Continuing with the mathematical model results, the power draw of the segment calculations were obtained by Morrell's model and Austin power model. So the Morrell power model calculates the power in the shell, cone, and when there is no load force, whereas Austin power model calculates the power only at the shell. We use these two equations to find the power in kilowatts. This is the bar graph representation of the Austin and model power model compared to DCS Fimiston model, where we also calculated the percentage error to understand the overestimation and underestimation of the power draw. That marks the end of the results section. To sum it up, the team built a mathematical model in MATLAB where we used first-order differential equations to calculate the power draw and mill content. The power draw results were obtained for Austin and model power model for analysis and comparisons against a Fimiston DCS model. Then the CAD drawings were designed according to the mill's specific requirements. Upon that, the team performed scenario-based vibrational analysis on the SAG mill model. Our team's future work involves testing and validation of the mathematical model to determine its predictive capacity, where we'll also be using vibrational analysis using wireless accelerometers to find out the vibration changes. Also, we'll conduct another experiment where we'll be using a flat liner, a degraded liner, to understand the behavior of the vibration and the sag mill. That's all for our presentation, and thank you very much.
Hopefully we've put you to sleep. Yeah.
Oh, we're so good.
We're that good?
It's quite nice topic. I'm guessing in a way you're trying to develop like a digital twin of a SAG mill. That's quite good.
Yep.
A couple of comments. I figured when you take both opposite liners out, you're probably not seeing too much difference because you've still got all the other lifters in there, which is keeping the balls turbulent, right?
Yep.
So it's probably not changing things too much. My only question is, when you take one of your liners out, that's a huge liner relative to the actual total liners in there, which you won't see in an industrial mill, because if you lose a liner, you lose a tonne or something out of your 300 tonnes worth of installed liners in there. So you may not see that such a difference. I'm not saying you won't, I'm just, what type of sensitivity do you think you can expect out of these type of sensors, and do you believe that you will see, let's say, a broken liner like that before the operations themselves would typically find it?
Well, our future work involves using wireless sensors, so we're trying to get something that's more sensitive so that we can perform more robust, we can collect more robust data and more sensitive data. So yes, you're right, that might not be the case, but we're also working on production of damaged liners, which we'll implement soon. So hopefully we get better results, yeah.
Thanks. Nice project, well done.
Thank you very much.
I'll just ask you, if Louw manages to gather another group of honours students for next year to work on a similar project, what would you recommend that they look at to follow up on this?
Well, what we did is we used a no-load system. We simulated something without any loads. Now, that's not how it works in real life. Obviously, it grinds stuff, so it needs things inside of it. So for future project, I would say they would have to try it with loads. That's basically what they have to do, yeah.
Loaded, wonderful.
Yeah.
Louw, we should talk for next year. Okay.
Thank you.
All right.
Right. Thanks for coming. You get presents too. Of course you get presents. There we go. Thanks, guys.
Next we have Dr. Difan Tang, a consortium postdoctoral research fellow from the School of Mechanical Engineering at the University of Adelaide. He is under the supervision of Dr. Lei Chen. Difan will be telling us about new sensor development for particle size measurements in hydrocyclones. Difan is always so serious that when he's actually telling a joke, people believe it's true. Difan? All yours. Yep, so green forward.
Ladies and gentlemen, I'm going to show you the next generation of particle percent passing size gauge for hydrocyclone overflow. Obviously, the objective of the project is to develop a new cost-effective sensing method to monitor the percent passing of a specified particle size online in real time for hydrocyclone overflow. As indicated in this chart, being a classification device, the hydrocyclone is part of a grinding circuit and also closely linked to the flotation circuit. At hydrocyclones, fine and light particles report to its overflow and proceed to flotation, while coarse and dense particles go to the underflow for regrinding. So it is important to monitor the particle size at hydrocyclone. In this project, we have developed a force measurement unit with a probe penetrating into the overflow pipe to measure the force from the incoming slurry. So we have found two types of interesting information from the force measurement. One is the particle probe impact dominated by coarse particles, and the other is the flow-induced drag dominated by fine particles. Coarse particles at hydrocyclone overflow have sizes generally similar to very, very fine table salt, and fine particles can be as fine as powder. So that tiny particles makes it very challenging to monitor their sizes. But we have found particles of different size distributions have their exclusive signature frequencies. And we have also identified the correlation between mass flow rate and the slurry of different size distributions. Eventually, we are able to tell the percent passing of a specified particle size in the slurry. Take P80, 75 microns, for example. The specified particle size is 75 microns, and our method will give you a reading in percentage, telling you the percentage of all the particles below 75 microns. So the outcome of this project will deliver several benefits to our end user. First of all, it gives you real-time monitoring of the particle percent passing of the specified particle size. So there's no need to wait for the offline analytical results. Secondly, this sensor can be easily integrated into a closed-loop circuit to fine-tune the operation of a grinding circuit, including mills and hydrocyclones. As we know, flotation requires the particles to be neither too small nor too big. So a closed-loop system will make that possible. It reduces the grinding task and also improves flotation efficiency in the meantime. Thirdly, the device is easy to use. You would expect as easy as push one button and just reading out one number. And the probe is made by durable materials. It can be replaced at the same time when hydrocyclone is due for maintenance. Last but not least, you will be looking at an expenditure, including maintenance cost, of less than 1/10 of the total cost of the other technologies. On a processing plant, normally there are at least dozens of hydrocyclones, and the number can be beyond 100 for big processing plant. So that means a huge savings. So the key behind the sensor is the analytical model. We've been building analytical models to predict the percent passing of a specified particle size by using force measurement. To help us understand the particle probe impact, we have done dry tests with sand in free fall from a certain height, as shown in this video. We've also done wet tests to use sand mixed in water to help us understand the impact from flow-induced drag. In this video, we use sand particle. The solid concentration is only around 1%, so you can still see the probe from outside. This is an example of our dry test. We can see the impact starts from around 3 seconds and ends at around 6 seconds. It can also be seen from the figure on the right-hand side, indicated by the highlighted area. That's the where the energy concentrate at around 40 Hertz. That's the resonant frequency of our probe. But we are also looking at more frequencies in the signals, like the image shown on the right-hand side. We call this signature frequency, and a particular size distribution can have multiple signature frequencies. This is another example in our dry test. We have used 6 classes of sand samples with narrow size distribution. Their signature frequency present themselves well in order, and we can see from the figure, the coarser particles tend to have high signature frequencies. So what does that mean? It means in real scenario, say slurry, it has a wide size distribution, so it has different signature frequency, different from here. But whenever the distribution change in the slurry, the frequency will shift. So by telling how much the frequency shifts and to what direction it shifts, we can tell how the size distribution change and to what extent. So we can observe similar things in our wet test, but in our wet test, we only test one type of sample. So it only has one size distribution, but we try to vary the mass flow rate, and we have found the signature frequency also vary with the mass flow rate. Now it's the most exciting part. As mentioned, we use one type of sand with a wide size distribution. That distribution is shown by the red curve, done by laser measurement with less than 1% residual error. And with our sensor measurement, we can reconstruct part of this red curve. But as you can see, the analytical model we have been building so far is not perfect, so it underestimates the percent passing of a given size. And also the error tends to increase when the particle size decreases. That's because when the particle size decreases, the flow-induced drag becomes dominant. And I believe we still need some work to do to improve our flow-induced drag model so that the error will be less, you can reduce the error when the particle size decreases. So in the next, we'll be testing higher concentrations, higher solid concentrations, and also different varieties of particles, and also try different locations of our sensors. As in this figure, there are 3 transparent sections. We are going to place the sensor on all these sections to see how it goes. And definitely we are going to refine our model to make it perfect. That's all of my presentation. Thank you very much for your attention.
Thank you, Difan. That was excellent.
Interesting topic. Just curious about the durability of the sensor. Normally in in mining applications, the slurry is quite abrasive. So do you have a feel for that?
Yeah, at the moment we are doing testing at the same time. We put the sensor into slurry and stir the slurry continuously. And we will test how much the wear would be and to estimate the lifetime of that probe. And currently we can tell it can serve at least 1.5 years.
That's pretty cool, thanks.
No problem.
Difan? How would the proposed method compare with the acoustic method? What would be the advantages?
The acoustic method is known to be very expensive. So the first benefit of our own method is the cost is just 1/10 of the cost of the acoustic one. And also, the acoustic only listen to the sound, but our method measure the force. Because the acoustic method and vibration method, basically, they're based on the same physical principle. They are all from vibration. But by detecting the vibration directly from the slurry, we know more information than the acoustic method. So that's why we can tell the fluid-induced drag and doing more things by using the flow-induced drag model.
Thank you.
Have you looked at this at different flow rates? So you've tried different sizes. What about different flow rates? Because I can imagine as the flow rate increases, the actual number of impacts for any given time on the sensor increases. I'd be interested to know how that actually affects the frequency itself of your sensor.
Yeah, as shown in the wet test, when we increase the flow rate from 320 liters per minute to 720 liters per minute, the signature frequency increases. Does that answer your question?
And you're able to take that into account with your calculations, it's all good?
Yeah.
Yeah, okay. Thank you.
No problem, thank you.
So you have to measure flow rate at the same time to calibrate?
Yeah, the flow rate is measured by another model, but not from the signature frequency. But we are comparing both.
Right, well, thank you very much, Difan. Thank you. Bismark Amankwaa-Kyeremeh is a PhD student at the Future Industries Institute at the University of South Australia, and he will be telling us about sensing and optimisation of flotation circuits and its integration with grinding. Bismark has a Bachelor of Science with Honours in Minerals Engineering from the University of Mines and Technology in Ghana. His research interests include froth flotation and the application of machine learning in froth flotation operation. Bismark enjoys listening to music and trying new spicy foods. Bismark. I'll put this up for you.
Thank you, Ruth, for the precise introduction. Hello, everyone, and welcome to my presentation. Today I'll be talking about sensing and optimization of flotation circuits with their integration with grinding. This project is supervised by Richmond Asamoah, Bill Skinner, and Max. I also have Christopher Grit and Meredith Lambert from BHP and Magato as my end-user advisors. So just a bit of introduction. Froth flotation has been the main separation technique that has ensured the sustenance of copper on the resource market. And to break it down is basically the separation of minerals based on the difference in their surface wettability. So the main aim of this project is to have an improved, stabilized, and cost-effective flotation process. And that is where the project sits among other projects in the consortium. Okay, good. So these are some of the main key findings that we have since the commencement of the project. And the first one is that Gaussian process regression model can make good rougher flotation recovery and rougher copper concentrate grade prediction using relevant rougher flotation variables. And then another main key finding is that Pareto search algorithm can find the best set of solution for the maximization of both rougher copper recovery and rougher copper concentrate grade. So why are these findings important? These findings are important because the developed models could be used to simulate rougher copper.
Don't move too far from
Oh, okay, that's fine. The importance of these findings is that the developed models could be used to simulate rougher copper recovery and rougher copper concentrate grade, and that will give a fair idea of what we are to expect from the operation. Aside from that, the optimum values that we have so far, operating them will see to a more stabilized flotation performance. So this slide talks about the study area where we have the red box over there. That is the rougher circuit, and these are the variables that are mostly monitored at BHP Olympic Dam to ensure that we have a maximum rougher copper recovery at or above a targeted rougher copper concentrate grade. So for this study, we use rougher copper recovery and rougher copper concentrate grade as the main output variables, with all other flotation variables as input variables. So this is what we did. We collected 80,000 observations on 15 rougher flotation variables with their corresponding timestamp recovery and grade data from BHP Olympic Dam. And as a usual practice, we had to do a bit of pre-processing to get rid of unwanted data set. So after this, we randomly selected 30,000 observations. And the purpose of selecting that was to cut down the computational cost that comes with dealing with large data sets. So the 30,000 observations were randomly partitioned into 80% training data set and 20% validation data set. And then the remaining portion of the data set was used as a testing data set. From here, the pre-processed data was subjected to Gaussian process regression algorithm, and the main idea is to establish relationship between all the input variables and each output variable in terms of the recovery and grade. So basically what the Gaussian process algorithm does is that it learns the relationship between an input variable or a set of input variables and an output variables, and based on this relationship, it's able to make new prediction when a new set of input data is subjected to it. So from there, we assess the model that we developed over there using correlation coefficient, relative root mean square error, mean absolute percentage error, and then relative error corrections. So this was done by computing the difference between the true and predicted values. For a very good performing model, we expect the R values to be approaching 1. In terms of the root mean square error and then mean absolute percentage errors, we expect very low values with values approaching 0. And in terms of the relative error corrections, we expect values approaching 100%. So based on the assessment, the predictive function of the best performing models were extracted as the objective function for the maximization of rougher copper recovery and rougher copper concentrate grade using these two multi-objective optimization algorithms. That is Pareto search algorithm and then multi-objective genetic algorithm. So let me break this one down because it's a bit technical. The main idea is for these two algorithms to find the non-dominant front or solutions so that one objective function cannot be improved without compromising on the quality of the other. So in basic terms, it searches for that sweet spot, said that the goal of each objective function can be found simultaneously without compromise. So this is the summary of the model performance. As you can see from the table, assessment using the various indicators shows that our models are actually doing very well. And to the extreme left of this slide is just a visualization of the true and predicted rougher copper recovery values using the testing data set. And this is the visualization of true and predicted rougher copper concentrate grade using the testing data set. We didn't present everything on this slide. So we needed to select the best multi-objective algorithm for this work. And we investigated 70 Pareto front solutions. And out of the 70, the best 4 were selected for each algorithm based on a rougher copper recovery constraint of at least 93%. So based on that, we investigated the best 4 from each algorithm. And looking at this image here, we can see a similar trend. However, if you look at the Pareto search algorithm, it lies slightly above that of the multi-objective genetic algorithm, which makes it a better choice in finding the best solution for the optimization of rougher copper recovery and rougher copper concentrate grid. So based on this, we focused our attention on the Pareto search algorithm in further investigations. Okay, don't worry about the figures. So from this table here, we can see that there is an inverse relationship between rougher copper recovery and rougher copper concentrate grade. So in layman terms, it means that the conditions that actually will see to the maximization of rougher copper recovery are the same conditions that are going to reduce your grade. So in order to select the best set of solutions, there should be a proper trade-off between recovery and grade with emphasis on variables that have economic impact on the process. So what we did was to carry out a hypothetical analysis considering all the set of solutions. And this work was done considering a 24-hour period. And then we imagined, or we considered a copper value of 9,254 per ton of copper. And then we assigned reagent values in terms of $1.20 per liter of xanthate and $1.30 per liter of water. And based on our analysis, we can clearly see that operating the plant or running the rougher circuit with solution 4 will actually see to a higher net gain in the period of 24 hours. And based on that, we selected solution 4 as our best set of solution for the maximization of both rougher copper recovery and rougher copper concentrate grade. So even though we were able to ascertain the optimal operating values of the various variables, but we realized that on a typical plant operation, it's very difficult to keep some variables at their optimal or at a fixed value. And these variables were feed grade and then feed particle size. So what we did was that, okay, let's keep all the other flotation variables at their determined optimum values. And then we try to vary feed grade and feed particle size simultaneously to look at their impact on recovery and grade. And when we did that, we realized that we are still able to have a value of 93.48 to about 93.67% in terms of rougher copper recovery. We did the same thing for the grade, and we had a value of 15.69% to 17.4% for the grade as well. So going forward, upon literature and the model that we have come across so far, we realized that most of them do not incorporate pop chemistry data. So at the moment, we have the Magatop pop chemistry monitor at BHP sites, and the main idea is to collect pop chemistry data in terms of the pH, EH, dissolved oxygen, oxygen demand, and then temperature. And the main idea is to now integrate the pop chemistry into the existing model to see how the models are going to perform in terms of their accuracy in predicting rougher copper recovery and rougher copper concentrate grade. Aside from that, we intend to carry out some laboratory experiments using ore from BHP Olympic Dam to see how the model is going to perform when we go to the extreme end of their various set constraints on site. At this point, I would like to acknowledge my supervisors, Kathy Eric, Christopher Grit, and Meredith Lambert, all from BHP and Magato. Thank you very much for your attention. All questions are welcome.
Bismark. I guess from your findings, would you say that set and forget the best parameters could be the best option for us outside instead of having that want to change and try different things, that maybe we should change less and watch?
Can you repeat your question again?
Your best set of parameters from model 4 gave you a very good recovery no matter how far you varied feed or particle sizing. So is that your conclusion, that we should just set the best parameters and not change them?
No, so if you look at, just a minute. These are the constraints that we use for the optimization, and these are values that I had from Kana. So normally, he said you operate within these bounds. So we try to give or use these constraints. So the algorithm were to find solution within these specified constraints. So what we did with the varying feed particle size and feed grade was to try and then keep all the variables at their optimum values as found by the algorithm, and then vary the feed particle size and grade within the same constraint. So we are not going outside what you guys do, but we are trying to keep within the bounds, like a typical operation, like what you do on site, and see how it's going to affect the process.
So you're saying we can keep using a model?
Yeah.
Yeah, thanks, Bismark. Do you expect or intend to build any other ore quality parameters into your model?
I don't know how far time will permit me, but then based on the studies that we've carried out, we are confident that the variables that we are currently considering as input variables are good enough to predict the outcome of the process. And then, like I said, one major thing that we have also found out is that most of the models do not incorporate pop chemistry data. So for now, and with the time that I have with my project, the only consideration that we are going to give attention to will be the pop chemistry parameters.
Do you think mineralogy would play a role, perhaps?
Hopefully. So for now, we are only considering the copper grade and no other, because initially we had about 25 parameters from site, which came along with a lot of mineralogy, mineralogical data as well, and we carried out feature selection, and out of that we realized that we can still make very good prediction with the existing input variables that we have. So going forward.
It would make a slight difference. And I think were they given the XRD data?
Probably.
Yeah, XRD data for that's crap. Sorry. But we do see subtle differences in the recovery when you're floating more chalcopyrite-rich material versus the chalcocite bornite. And there actually are noticeable differences. But given a constant mineralogy going through, I think your stuff is pretty good.
Thank you.
Thank you, Bismark. Oh, here we go. Pull this down. How are we all going with our lunch digestion? If you're able, perhaps stand up in your seat where you are. Online people can join in. Stand up, give yourselves a bit of a shake, have a jump around. Push that lunch down. Okay, and now we're ready for the next few talks. Everyone take your seats. So next I'd like to introduce Linda Rozenberga, a PhD candidate at the Future Industries Institute at the University of South Australia. Linda's project is metal organic framework-based fibre optic sensors. Linda was born in Latvia and moved to Australia almost 4 years ago after living in the UK for a couple of years. Her hobbies include travelling, camping and gardening and drawing, and she's always looking for a new hobby or DIY project. Linda.
everyone. My name is Linda, and I am a PhD student at UniSA. And my project is on developing a new metal organic framework-based optical fiber sensor. And the objective of this project is to develop a fluorescence-based sensor for measurement and detection of ferric ion in water and solutions. Fluorescence is the ability of some materials to absorb the light and re-emit it at a different wavelength. And fluorescence sensors use this property by altering the light that has been emitted in order to tell us how much analyte we have in the solution. And fluorescence sensors have the benefit of being very accurate, very fast, and very sensitive. And so to develop a new sensor, we split up this project into 3 stages. The first one was finding the right sensor molecule for our target application, and we chose to use metal organic frameworks, or MOFs in short. Metal organic frameworks have large complex structures, and some of them have excellent fluorescence properties and are promising sensors. Then to obtain a solid state sensor, we developed a polymer MOF composite that would hold the sensor particles in place and also significantly improve the sensor properties. Then the last stage is developing the actual prototype of the ferric ion sensor by coating optical fiber with this composite and developing the overall sensor setup. The target application for this sensor is mineral processing, specifically mineral leaching process. It's a chemical reaction during which ore is dissolved to extract our target mineral. And in case of copper, uranium, gold, and zinc leaching, ferric ion plays an important role. It determines how quickly the mineral recovering is occurring, and therefore, if we know the concentration of the ferric ion, we can control it, optimize it, and it can be very beneficial towards this process. However, this prototype sensor could not only be used in mineral processing, but also to control the drinking water quality. Too much ferric ion can negatively affect the drinking water by giving it unpleasant color and affecting human health. This sensor can also be used in medical field to assess the ferric ion concentration in human body, and therefore prevent anemia, Parkinson's disease, and Alzheimer's disease. Could also potentially be used in wastewater treatment processes. Too much ferric ion released environment can cause the death of aquatic plants and animals and promote the bacteria and algae growth. However, the target applications are not the only reason why we need a new ferric ion sensor. The current methods that measure the concentration of ferric ion have several drawbacks. For example, none of them can provide us with real-time monitoring of the concentration of the ion in water and solutions. They are affected by other ions. They do not determine the ferric ion concentration directly in many different methods, and the process relies on sampling, which means that samples need to be extensively pre-treated, and the equipment to analyze it is very expensive. Fluorescence-based sensor hopefully would address most of these drawbacks and wouldn't have them. Next, there are many different fluorescence sensors out there that could potentially be used for ferric ion concentration measurements. And they also have several drawbacks, especially if we're considering the use in mineral leaching processes. So for example, they can have poor selectivity, they can be toxic, have background noise, or poor pH stability. Metal organic frameworks do not have these drawbacks. They're stable, they're selective, and they're highly versatile, meaning that no two MOFs are the same, and we can tailor the properties of the MOF for our intended application. So in order to develop this sensor, what we did was we looked at the literature, and we picked out a few potential ferric ion sensors and synthesized them. Then we chose the most promising one, and we performed in-depth study on its stability and properties to understand what they can and can't do. Then we were looking at how do we take this MOF powder and turn it into a coating. And we ended up developing a new MOF polymer composite that would be compatible with our intended application and would also improve the properties of the MOF sensor itself. Then lastly, we developed a method of how to transfer this composite onto an optical fiber as a coating and develop the overall sensor setup. So in the first stage of this PhD project, we were looking at different metal organic frameworks, and we ended up going with a European-based MOF, which means that this MOF has a European metal center surrounded by organic acid. And when we performed the in-depth study on it, we found new data on its structure and properties. We found out that it is not only fluorescent sensor for ferric ions, but also for pH. It's very selective towards ferric ions, has good pH and thermal stability, and we also managed to improve the synthesis yield by 50%. Then when we developed the MOF polymer composite, we found out that it significantly improved the fluorescence intensity and properties by having it encapsulated in the polymer matrix. So if we look at the graph in the middle, this is a typical fluorescence spectra of the material that I'm using as a sensor. In purple, we can see the European MOF powder suspension in water spectra. And when we want to measure the ferric ion concentration, we would see the peak at 430 in purple decreasing as the concentration increases. However, when we have the MOF encapsulated in polymer, we can see this fluorescence spectra in green. We have now 3 new, very strong distinct peaks, all acting as ferric ion sensor, and the intensity is significantly increased. And as a result, we managed to increase the sensing range of this sensor almost 10 times, and we increased the selectivity of the sensor. So now it's no longer pH and ferric ion sensor, but only ferric ion sensor. And it showed very good MOF retention in the polymer matrix and very promising reusability. Now the last stage is coating optical fiber to make this sensor practically and easily used. So we take optical fiber core and we coat it with a composite that we have developed. Then we attach light guiding fiber on each end of this coated fiber. And when we want to make a measurement of ferric ion concentration, we dip the coated part in our target solution, and we have a laser source emitting light at specific wavelength. Then the light guiding fiber is guiding this light down to our sensor coating. The sensor coating absorbs the light and re-emits it at specific wavelength and intensity. And then the signal is taken to spectrometer and computer, and the signal is analyzed. So what we would see is difference in intensity in the signal based on how much ferric ion we have in the solution. Now, at the moment, we are working on finalizing the prototype sensor and assessing its full performance and adapting it for use in our target applications. Then, in future, for this specific prototype, we can look at how can we optimize the sensor setup so that it's more portable and easy to use, and also how can we optimize the optical fiber coating process to make it quicker and more cost-effective. And lastly, long-term, the methods that we have developed for the composite fabrication and coating of optical fibers is an excellent base for developing new MOF-based sensors. So in future, we can potentially have a bundle of fibers, each one measuring different analytes in solutions. So I would like to thank my supervisors, David Beatty, Marta Krasovska, Vital Block, William Skinner, David Lancaster, and Christopher Greed for their guidance in this project, and also Anton Blenko and Todd Gillam for their help with developing MOF polymer composite, as well as research groups at UniSA and Adelaide Uni. And thank you for the attention.
Any questions, Belinda? Tom?
Yeah, is your emission very sensitive to changes in your excitation source? So if your laser wavelength changed because of ambient temperature variations, would your emission intensity change as well?
It is sensitive to it, but only if it changes by more than 20 nanometers. So as far as I have looked at it, temperature hasn't been an issue.
Linda, great work. Just wondering, I know you haven't mentioned it, but maybe from former presentations, how did you go with the pH limitation at acidic environment? Other than that, it's like a really good finding and sensor anyway. Like, it's a great technology. If that didn't work, and then yeah, like that polymer coating, I think is quite new results for me to see. So yeah, it's really exciting to see that improvement just from how you've composed the coating.
Yeah, thank you. Yeah, the polymer composite results were somewhat unexpected. I didn't expect them to be quite as good and improve the sensor as much. But as far as the pH goes, so what we are looking at doing is actually developing a sample pre-treatment procedure so that we could actually apply the sensor for mineral leaching. So what we're looking at is how do we bring up the pH slightly so that it is in the range where we can use the sensor. So sensor limitation is about 2.4 pH. Below that, it will break down. So if we bring up the solution pH higher to this level, we can measure the ferric ion concentration. And the good thing is with ferric ion, if the pH is too high, it would precipitate as ferric hydroxide. However, that doesn't happen unless the pH is above 4.2. So as long as we are aiming, let's say, for pH 3, we can use it in mineral leaching processes and in acidic environments with a simple dilution process to bring up the pH.
Last question. Is the europium fiber very expensive to make?
Surprisingly, no, because optical fibers themselves are quite small, so we end up using very, very small amounts of europium. So the prototypes I'm developing at the moment, it's anywhere between 0.5 to 2 milligrams, which is less than a typical TV, for example, would have, or any monitor would have. So a one fiber, at my current estimate in materials, would cost less than $10 to make. But that doesn't involve the work and the equipment that comes with actually making it.
Okay, understood. I just wonder if it was going to sort of dynamically upset the rare earths market or something.
It shouldn't, no.
Okay, thank you.
Thank you.
Everyone's trying to avoid chocolates. So Kirsten Louw is a PhD candidate at the University of South Australia, and her project is diffusive processes in mineral processing. Kirsten is from South Africa, and after completing her master's degree, Kirsten worked in banking for 4 years, taught English in China for a year, and has now returned to academia in Australia. The South African melting pot of culture has influenced her love of travelling, experiencing new cultures, and eating tasty foods. Kirsten.
Thank you, Ruth. And hello, everybody. So I am an applied mathematician, and a lot of my work is relatively new to most of you, so I hope you can follow me. My project falls in the research group 3 under leaching, and it's closely linked to Linda's work. When Linda is creating a ferric ion sensor, I am investigating I am providing theoretical insight as to how ferric ions interact with the sensor. And to provide this insight, I need to have a fundamental understanding of the system. And so when looking at the microenvironment, the ferric ions interacting with the MOF crystals, we need to know how they interact and how they bond. And this is looking at the van der Waals forces between the ferric ions and the MOF crystals. And what we found out is that the ferric ions, the hydrated ferric ions, are attracted to the MOF crystals, but are too big to fit inside the pores. And then we need to understand the macro environment, how the ferric ions diffuse through the solution and through the polymer. So the sensor will be submerged into a solution containing hydrated ferric ions, and we see how the ferric ion moves through the solution and through the polymer. Here we have preliminary results as to how long to expose the sensor to the solution, and so we know when the MOF crystal reaches a stable state of ferric ion saturation. Why this is important, there we go, okay. Why this is important is that, firstly, we know that the ferric ions do not fit inside the pore, so this is surface level bonding. This means that if we want to wash the sensor, we can, and the ferric ions are easily removed from it, and we can reuse the sensor and less wastage. And if we know how long to leave the sensor exposed to the solution for, we find critical time. So we don't expose it for too long of a time period, so that there's less time wastage. Today I'm only focusing on the first aim because this is where we have completed work, and we are still investigating the second finding. As a mathematician, I use already well-established physical laws to describe systems. And in this case, to describe the microenvironment, we are using the Lennon-Jones potential to describe to find the potential energy between two atoms, and in our case, between the hydrated ferric ion and the MOF crystal. So we have the Lennon-Jones potential given as U of rho, where rho is the distance between two atoms. I'm too close to the speaker, or let me just move it up a bit. So rho is the distance between two atoms, and when atoms are very close together, they experience repulsion, and then as they move further apart, they reach a distance, sigma is the van der Waals diameter, and this is where the potential energy is 0, and as they move further and further apart, they reach a potential energy minimum given at rho naught. And here, the potential energy is denoted by epsilon. And then from here on out, we experience attraction. But this is only between two atoms, and we want to know the interaction energy between the MOF and the hydrated ferric ion. And we are assuming a continuum approach. For the MOF, we isolate a pore, and we are approximating the MOF pore with a cylinder, and we're smoothing the atoms across the surface of this cylinder. And for the hydrated ferric ion, we have the ferric ion in the center, and we have water molecules surrounding it, oxygen in red, hydrogen in white. So we're approximating the hydrated ferric ion with a point and two concentric spheres with an inner oxygen shell and an outer hydrogen shell. Previously, I showed you an equation for two interacting atoms. Now we want to look at, in particular, the ferric ion interacting with the MOF pore. Here we have the ferric ion sitting on the x-axis, and in the negative direction, x is negative, the ferric ion is away from the MOF pore. The MOF pore's entrance is located at x is equal to 0, and so when the ferric ion moves into the MOF pore, this is in the positive direction into the MOF pore. To calculate the interaction energy, we're just going to isolate one instance, so the oxygen found in the MOF pore. So the oxygen atoms are smooth across the cylinder, and we want to know how this ferric ion interacts with each point on the cylinder. And then we integrate the interaction energy over the surface of the MOF pore. And then to calculate the total interaction energy of the ferric ion to the MOF, we do the same calculation with all atom types found in the MOF pore, so oxygen, hydrogen, carbon, and europium. Then we can consider the oxygen sphere. Now, instead of a point, we have a sphere, so we're calculating the interaction energy on every point on the sphere to every point on the cylinder, and we integrate that over both surfaces, the oxygen sphere and the MOF cylinder. And again, we account for the different atom types found in the MOF pore to get the overall interaction energy between the oxygen sphere and the MOF pore. And we do the same process for the hydrogen sphere. And then we have the sum total of the interaction energy. So we have with our ferric ion to the MOF pore, oxygen sphere to the MOF pore, and hydrogen sphere to the MOF pore. And if we know the interaction energy, we can also calculate the interacting forces. And here we have our results. So on the left-hand side, we have the potential energy, the interaction energy between the ferric ion, hydrated ferric ion. The sum total is given by the black line. And on the right-hand side, we have the interaction force. And again, the sum total in the black line. On the x-axis, this is the ferric ion's relative position to the MOF pore's entrance. So to the left-hand side, we have the ferric ion, or the hydrated ferric ion, away from the MOF pore, and to the right, in the positive direction, it is into the MOF pore. And we see that looking at the potential energy, there is a potential energy minimum inside the MOF pore. So it is favorable for the hydrated ferric ion to be inside the MOF pore. And when we're looking at the interaction force, we see that force is greatest at the entrance where x is equal to 0. So force has magnitude and it has direction. So when force is positive, it is directed to the right. It is attracted to the MOF pore. The hydrated ferric ion is attracted to the MOF pore. But atoms are not points. They are, they have space. They occupy space. And the entire ion cannot fit inside the MOF pore. But we do know it is attracted and where it is attracted, and it responds to the MOF pore. Right. So we have completed our findings for the first instance and have written up a paper and is ready to submit. We are currently working on the second finding, and we have preliminary results for our one-dimensional problem. And here we are using mathematical models to describe the ferric ion concentration and the MOF occupancy of the MOF occupancy, so how many ferric ions are bonded to the MOF crystal as time passes. And here we build on physical characteristics onto the model. And then we are going to follow up from experimentalists where we find critical times, and we can suggest this to the experimentalists. And so this will give them better insight as to how to further develop the ferric ion sensor. And I would like to thank my supervisor, Bronwyn, and my supervisory team, Linda, and one of her co-supervisors, the state government, UniSA, and PRIF. Thank you.
Thank you, Kirsten.
Thank you,
I was waiting
Ruth.
for you to lose me there, but I actually followed you the whole way.
Oh.
Has anyone got any questions? Oh.
Yeah, thanks, Kirsten. That was really good. And as a physicist, it's great to see spheres operating in a pseudo-vacuum. I have a question, though. There didn't seem too much sensitivity in your model to ferric ion, and it was rather to the hydration of the ion for the MOF. The attractive force was dominated by the oxygen and hydrogen.
Mm-hmm.
Is that a concern? Do we know that we know that the MOF is sensitive to ferric, but your model doesn't show much sensitivity to ferric itself?
No, is my initial guess. I don't know too much chemistry, so bear with me. So from what I know is that the ferric ion is not by itself, by its lonesome in the solution, and its general state is to be hydrated. So if it was hypothetically, it would still be attracted. It's just that, as you said, that the water molecules do overpower the interaction. But that's not a bad thing. Yeah.
That's yeah.
Could you perhaps just give us a little bit more detail of how your results feed into Linda's project, to tie the two together?
So it mostly comes from the critical time. So when we have more information from the second part, how long to leave the sensor in, we can also determine how thick the sensor coating should be, although that's not really written on there. And that we can give to Linda. So Linda doesn't have to go through trial and error in terms of testing what are preferential times or preferential sensor or coating thickness.
Thank you.
Time for one last question?
Oh.
I'm excited about it. Okay, run away, Kirsten.
Oh, thank you.
So we'll now have a 15-minute afternoon tea break. So we will reconvene at 3:15, just to round it off. So we'll then finish off with Program B of the consortium. Thank you.